Okay, welcome to this class on numerical methods for physical modeling. So what we're going to be focusing on here is what's called numerical analysis. And the basic premise behind numerical analysis is the study of methods or algorithms for solving problems from continuous mathematics. Okay, so the study of methods or algorithms for approximately solving problems from continuous mathematics. Okay, the basic process, if you will, is that you start, in some sense, with a real-world problem. Okay, and then we do some sort of mathematical modeling. And the goal of this is to, in some sense, abstract the real-world problem into sort of a more well-defined mathematical problem. And then once you have this mathematical problem, you develop a numerical method in order to approximate the solution of this. Okay, so you have a numerical method. This gives you an approximate problem. Sorry, gives you an approximate problem. And then what happens then is that you do some sort of scientific computing. To give you an approximate answer. And oftentimes it's like the distinction between sort of the numerical method and the scientific computing is oftentimes blurred. But it is fruitful in many cases to take a sort of precise mathematical problem and approximate it. And then oftentimes what happens is that the exact or a very reasonable approximation of the approximate problem is that solution is a good approximation of the exact answer of this mathematical idealization. Okay. In any case, it's like once you've done this, you're not quite done yet. It's always important to do the last step, which is to compare your approximate answer back, or try to interpret it back into your real-world problem, and to see whether or not it's reasonable through some sort of process of validation. Okay, and then again, ideally, it's like what happens is that it's like each of these sort of parts of the cycle, if you will, introduces potentially some sort of error. It's like when you introduce some sort of approximation. Okay, so when you finally come back up to the approximate answer and then try to reinterpret it back in the real world, you'll have to decide whether or not that approximate answer is accurate enough for your application. And if not, you have to iterate the process and try to maybe incorporate some additional physics which you were missing in your sort of abstract mathematical model to begin with, or do something that's like sort of more precise and more accurate. It's like in the approximation steps in actually trying to derive a approximate or numerical solution of the problem. Okay, So, but in any process, it's there's always this idea of a feedback cycle or feedback loop when you're doing modeling, simulation, numerical approximation, to try to make sure that the answer which you get or the approximation which you obtain is good enough. It's like for your application. And again, if it's not good enough, it's like then you have to iterate the process and try to improve the approximations in some way, shape, or form. Okay. All right. So let me say a little bit about what we're going to be doing in this class. Okay. Again, with this kind of picture in mind. So we're going to, so the focus of the course. So the first thing we're going to do is we're going to start with a class of mathematical problems. So we're going to consider a class of mathematical problems. Okay. And then we're going to sort of introduce numerical methods which are applicable to the class of problems. Okay, so we're going to devise a method to approximate the problem, to approximately solve the problem. Okay, and then the next thing we're going to do is we're going to analyze this. This is sort of where the numerical analysis comes in. Right, so we're going to analyze the accuracy of the method, its stability, and failure modes of the method. So what we mean by that is that we'd like to know what kind of errors it's like are made or introduced when you use a numerical method, right? How robust or stable it is. Do small changes it's like in the data in some way, shape, or form result in large changes in the numerical answer which you get, right? If that is, it's like then the problem isn't well conditioned or well posed, and so you have to be aware of that. And again, it's also important, for most numerical methods and most mathematical methods in general, that there are sort of underlying assumptions, it's like upon which the methods or the techniques are built upon. And when you violate those assumptions, oftentimes it's like you have failure, it's like of the method. And so it's important to understand not just how good the method is in terms of its accuracy and its reliability, but also when it fails, okay, so that you know when to avoid it, okay. And again, the bottom line is the following: you don't want to look at these methods as black boxes and just take the results for granted. You want to make sure that you understand these methods enough that you can anticipate when, on the one hand, what are good methods based on the particular characteristics of the problem you're studying, as well as, when you should not, when you should be, shall we say, more cautious about the answers you get, and when you need to validate it a bit more carefully. Okay, and then finally, it's like one aspect that's like which we're also going to focus on. It's like in this class is not just doing the analysis, but actually implementing this method on the computer so that you actually see how to do that efficiently and see how it performs in practice. Okay, so we're going to implement this method as well. All right. So, so this is a upper division class on numerical methods and with a flavor of numerical analysis. So what we're going to do next is introduce some of the underlying theorems, from calculus, which is going to be relevant in the analysis of some of these methods. So let me just stop here for now 1 second, and I'll introduce these theorems in a little bit.